So the next speaker is also from University of Western Cape, but a PhD student. So that's brilliant. So Cebo Ngwetsheni. Apologies for my pronunciation. So over to you to tell us about shell effects at high excitation energies.
All right. Okay. It's let me start sharing screen first.
Here we go.
And there we go. So it's a Ngwetsheni, Cebo, supervised by Nico. So I'll be discussing the continuation of shell effects at high excitation energies, quasi-continuum. So we discussed this using polarizability. First, we describe what is polarizability. Most of it is what Nico has gone through in his talk, so I'll be repeating it again in my own version. So nuclear polarizability is governed by the dynamics of the giant dipole resonance, which is the main parameter being the symmetry energy. From the hydrodynamic model, you can imagine it is an interpenetration of neutron and proton fluids out of phase, like that there. And it is governed, as I mentioned already, by the symmetry energy parameter. So we have two descriptions, the macroscopic part and the microscopic part. Macroscopic being from the liquid drop model, having the power law there from Migdal, which assumes a well-defined nuclear surface, which is different from the second interpretation, which is using quantum mechanics from second order perturbation theory. We have the polarizability being proportional to the second moment of the total cross-sections. The total cross-section in this case may include photon-neutron cross-section, and is weighted by the gamma energy, which is a transition energy between your states there, from initial state I to a particular state up there in the excitation state, and going down to the ground state. So the symmetry energy also has a mass dependence from the liquid drop model. We did these calculations using three methods from sigma minus 2 values, GTR parameters, binding energies, and then we have the overall trend, which shows that the symmetry energy is actually low, going lower for lower masses, and saturates at about 23, 24 MeV for heavy mass nuclei. So all these three methods are in agreement. From this, then we have the sigma minus 2 dependence, or dependence on symmetry energy, which also explains how the sigma minus 2 for the low masses is enhanced there. There's various versions of this liquid drop model that we will see later. Okay. So naturally, the complete picture of the polarizability, dipole polarizability, should include both electric and magnetic contributions. The electric part, which is what we discussed before, and then the magnetic part is dependent on both paramagnetic and diamagnetic susceptibilities, where the susceptibilities are dependent on transitions between states, which mostly the paramagnetic part explaining is mostly influencing the low mass nuclei, and then the diamagnetic part is mostly dominant in heavy mass nuclei, like for A greater than 60, that is where it is dominant. So it is of interest for us now to continue investigating what is the influence of these paramagnetic susceptibilities on the total sigma minus 2 values. And now we come to the phenomena of interest for my talk, which is the low energy enhancement, which is basically an upband observed in photon strength functions that are measured mostly in Oslo. So what we expect for the standard model is that, not the standard model, but the Lorentzian distribution, which model the gamma strength function. is that as you go down in energies, approaching zero, the strength should also be approaching zero, but the observations and the experimental observations show the contrary to that case, which we see the enhancement of the strength function. So to interpret this, there's two models, one being the shell model and the RPA model, which says that these strength functions, these enhanced strength come from transitions between states in the quasi-continuum region. And the M1 predicts that these are just magnetic dipole transitions which occur between proton and neutron orbits. So with this said, then we come to the aim of the study. Because of the sensitivity of sigma minus 2 values to the transition energy, E gamma squared there, we wanted now to investigate what could be the effect of this low energy enhancement on the polarizability or sigma minus 2 values. So we do this by, first by extrapolating down to 0.1 and 0.8 MeV. This is supported by the recent calculations of strength functions from shell model. Shell model predicts that enhancement continues down to 0 MeV. So what we did in our case, we extrapolated these strength functions down to 0.8 MeV. These are our results. No, not yet. Okay, this is how we do it. First, we convert the cross-section, the strength function, to cross-section, dipole cross-section. So we can be able to combine it with the giant dipole resonance cross-section. So this is supported by the brink-Axel hypothesis, which says that the GDR is actually independent of where it is measured. It is just dependent on the E gamma transitions. As you can see, the example here for neptunium-238, we have the probability per channel, which is proportional to the strength function, which we see that there's the properties of the GDR, which is the resonance energy, the strength of the resonance is maintained at various, when measured at various excitation energies from 2.9 up to 5 MeV, with the width of the resonance becoming wider as you go up in the excitation energies. So this, from it here, we infer that the GDR origin is similar between whether it's measured in the ground state or excited energies. And you can see here that when we mesh these two cross sections, they match nicely without having to be normalized. And then they fit with the cubic spline. You can see we have various fits here. The correct one being the cubic spline in blue there. The quadratic one not working well. And then for completeness, we also include the gamma P cross section on top of the gamma N and then gamma N plus P cross section. So what we observe is that for lower mass nuclei, the contribution is larger, and as you go up in mass, the contribution of the low energy enhancement becomes lower. But we also note that for the semi-magic nuclei like vanadium, lanthanum, and zirconium, we see that the sigma minus 2 is dropping down there compared to the neighboring nuclei, which now from here we can infer that the shell effects are continuing at high excitation energies, as we say that the low energy enhancement occurs at high excitation energies. So from there we say that also the shell model, of course, remains valid at high excitation energies also, and they will support the M1 nature of the shell model of the low energy enhancement. So now these conclusions now say that we can now use sigma minus 2 as a new spectroscopic probe to search for new and old magic numbers. That is, we can use sigma minus 2 to verify the magic numbers that we already know. Then the sigma minus, this work now further on that we need more measurements of the strength function at energies below 1 MeV, especially for the lower mass nuclei, that is from scandium going down. and above 153 samarium, which one measurement was done for lead 208 here, and then no enhancement was observed for that one. And now to further from here, we have ongoing investigation of the evaluation of the polarizability and its influence on the nuclear collectivity. So for that, we are going to investigate what is happening here. We see a lot of discrepancies with the Cebo-2 being obtained from various methods, from Kulik's shell model and photoneutron cross-section. So it would be interesting now to add gamma-p cross-sections here and investigate and compare now with experimental values. And from here, if we get these kappas or we evaluate how the kappa evolves as energy goes up, we can now constrain the symmetry energy, which means we'll verify, we'll see which model best fits our data. And so far, only for lithium-7 and oxygen-17, we have measured kappa. Kappa has been measured at the first excited state, which happens to be J pi is equal to half minus. We know for half minus states, the spectroscopic quadrupole moment, which is a second order effect, is 0 for J is equal to half and 0 states. So, which means that we expect the polarizability to be dominant in those states. So for this, we will we'll perform our experiments using the new array that is being worked on at Itemba, and do this Kulik's measurement for oxygen-17 and lithium-7 and oxygen-17. And intended proposal that is all there for 7 beryllium and fluorine-17, which is a mirror nuclei. So that is the state of our work so far. And thank you. That will be the end.
Oops, sorry, took me by surprise. Wait a minute. Thank you, Cebo. Sorry.
Yeah.
Too many buttons to press. So, excellent. Well, very clear presentation. I'll put your picture back up. We want to see you.
I wanted to okay, sure.
So we know what you look like. We can't meet you in the coffee lounge anymore.
Oh, I'm off.
It's okay. It's okay. Does anybody want to ask any questions via the chat line or directly? Just indicate on the chat line. Hi.
Yeah, I'd like to ask a question. Is that okay?
Yeah.
Okay. If I understood right, you are going to measure the low energy strength function for nucleus as light as 7 lithium. Now, does the concept of a giant dipole resonance really apply to as light a nucleus as 7 lithium?
Yes, we do observe the GDR for light nuclei also, and it mostly shows for those masses, we mostly observe that it is not as smooth as you would see for high masses, but we see some structural changes. But the giant dipole, as I would say, we do observe it for low mass nuclei also. And just for deuterium, that is not observable for.
Yeah, this is my difficulty with this. The other comment is that if you really want to address the symmetry energy change with temperature, I think it would be right to look at a wide range of isotopes of a heavy nucleus using stable and radioactive ion beams, isn't it? And to extrapolate from these light nuclei, I mean, this seems to be a little odd.
Well, for what we intend to do is check how kappa, which is the polarizability parameter, if it evolves in those low mass nuclei to address that those discrepancies there. I'm not sure if I'm answering your question or. We are not going to investigate the temperature, how it varies with temperature.
Okay. Thank you, Cebo. I think most people in South Africa will be desperate for their lunch now. So I just want to thank everybody, all four speakers, for that first scientific session of this conference. It's been fantastic, a great start. And thank you all. And I would like to hand over to Nico in case he has any announcements to make going forward.
No, John, thank you so much.
I should say, yeah? Nico, the discussion has been, it worked. It's excellent. And if, from my experience now, if the chair can just control who's speaking and when and that through the chat line, it works very well. And then, of course, you can carry on in your breakout groups if you work out to get into them, the chat after. So, yeah, that worked quite well.
Thank you so much. So I just wanted to answer Vivek a little bit, because that's a very important question, what he just brought up about, obviously, the GDRs in light nuclei, they are not so clear. However, this Coulomb excitation, as Cebo just mentioned, we have a second order effect, and we can determine whether there's any, there may be another second order effects, we don't know. But one is the reorientation effect, the quadruple moment. Another one is the reorientation effect. I mean, the nuclear polarizability. So any deviations, and this was done in Chalk River and the Australian National University, ANU, by Vermeer and Reyes-Pierre. So this was measured, the nuclear polarizability in these light nuclei, assuming always that the hydrodynamic model applies there, which is not clear to anyone. So that's something that we have to investigate as well. Thank you for the question. But right now,
so you're sure.